Chapter 3, Describing Data Using Numerical Measures. In this video, we'll learn how to compute a z-score as well as the coefficient of variation and how to use the empirical rule in Chezchevs Theorem. Recalled in the previous videos, we learned about the mean and standard deviation as the two most commonly used measures in business. The mean is a measure of center and location, whereas the standard deviation was a measure of variation. Together, this allows us to calculate something called the coefficient of variation. This is the ratio of the standard deviation to the mean, and it's always expressed as a percentage. It essentially shows us the variation relative to the mean and can be used to compare two or more sets of data that are measured in different units. So imagine if I wanted to compare the variation of test scores in a math class versus a Spanish class. Both classes will have different questions on their different exams and different students, but we can still use this formula and compare the variation of each group so we can see what might be impacting student performance, such as the way the teachers teach, or the time of the day of the class, or some other factor. So here we have our formulas, and you'll notice that the population coefficient of variation and the sample coefficient of variation are very similar in structure. The only difference is the Greek letters. So the Greek letters let you know, are we talking about populations? So here we have our population standard deviation, and here is our population mean. Whereas over on the sample side, we have a sample standard deviation in the lowercase s, and the sample mean with our x bar. Again, it's really important to learn these Greek letters so that you don't have to keep looking them up when we talk about them throughout the semester. But if you need a refresher, I do have a glossary of the Greek letters posted on our homepage in Canvas. So whether you're doing the coefficient of variation for a population or a sample, it's the same process. We'll first take our standard deviation divided by our mean, and then multiply it by 100 and make sure we've got the percent at the end. So let's go ahead and look at an example from our textbook, problem 50. You're given the following parameters for two populations. So we've got some data over here on the right. In part A, we want to first compute the coefficient of variation for each population or each group. So first we'll plug in our standard deviation for our first population. So make sure we get the right number in there. That's going to be our 50. We'll put that on top. And in the denominator, that's our mean, so we'll throw in the 700. So if you only plug the 50 divided by 700, you'll get 0.07 and some change. But we have to remember that we always have to write it as a percentage. That's why we multiply by the 100 to remind us to include the percentage sign at the end. Thus, our coefficient of variation for population 1 is 7%. Let's do the same thing for population 2. We'll take our standard deviation, that's the 5,000, and our mean of 29,000. Now, if you'll notice, the data points for our two populations are very different. Population 1 has small numbers when we compare it to population 2. That's why the coefficient of variation is so useful, because now we can compare the two groups even though they're very different in terms of their numbers. So if I take 5,000 divided by 29,000, I'll get 0.17, but we have to have it in percentage form. That's why we'll multiply it by the 100, and that gives us 17%. Now in part B, it asks which population is more variable relative to the size of the population mean. So more means greater. So which of my two coefficients of variations are greater? Population 2 is because it's got 17%, which is a higher number than our 7% from the population 1. The empirical rule is another useful rule to understand our data when our frequency distribution is bell-shaped. So recall in Chapter 2 when we were calculating frequency distributions, some of them were shaped symmetrically like a bell. So according to the empirical rule, our population mean is in the center here. And if I go up one standard deviation and down one standard deviation, that means 68% of my data falls right here in the middle. I can now describe where my numbers that I'm collecting will fall. So 68% of our data falls within one standard deviation of the mean. Then, if we go out two standard deviations up from the mean and two standard deviations down from the mean, that means 95% of all our data can be seen between these 2 points. And then if we go up 3 standard deviations out to the edge and down 3 standard deviations out to the edge, then this virtually has all of our numbers in our data set. Because if you have any number that is greater than 3 standard deviations away from the mean, these are considered outliers. So they're extremely small or extremely large in relation to our population mean. So let's look at an example of how we could use this rule to estimate our data. So imagine in San Diego that we've collected data on Uber rides, perhaps because you're interested in seeing if it's worth becoming an Uber driver. And it was found that our population mean is 15.1 miles per ride, and that the standard deviation is 3.1 miles. So we'll go ahead and plug in our mean and our standard deviation right here. So here's my mean of 15.1, plus or minus, plus because we're going up, and minus because we're going down. And one standard deviation is taking our 1 multiply by our standard deviation of 3.1. So then we'll take 15.1 plus, and when we multiply anything by 1, it's itself. So 15.1 plus 3.1 and 15.1 minus 3.1 is now going to tell me the typical range of data or miles per ride I can expect. In other words, 68% of our data values, or 68% of the rides that I will drive, is somewhere between 12 and 18.2 miles. Now I can actually estimate, see how many rides I can fit typically in a tank of gas, for instance. Now let's go ahead and go out 2 standard deviations. So here, I'll take my mean again of 15.1, plus or minus, since I'm 2 standard deviations out, I'm going to take 2 times my standard deviation of 3.1, and 2 times 3.1 is 6.2. So I'll take my 15.1 plus 6.2 and 15.1 minus 6.2, plus because I'm going up 2 standard deviations, and minus because we're going down by 2 standard deviations. So that'll give me a range that 95% of my Uber rides is somewhere between 8.9 miles and 21.3 miles. So it also gives me an estimate of how long my rides are if I'm an Uber driver. Chezchevs theorem is another useful rule of thumb, similar to the empirical rule. Note, though, that the empirical rule is only used for bell-shaped distributions, meaning they're symmetrical. Chezchevs theorem is for non-bell-shaped distributions. That means they could be curved or skewed in any direction. So it's much more conservative, and we can see here in our example that it's not symmetrical. It's not bell-shaped. It's skewed. And what it can tell us is that at least 75% of our data values are going to be within 2 standard deviations of the mean. So it's helpful if you just look right here. Here's my population mean, plus or minus my 2 standard deviations. That tells us 75% of our data is within 2 standard deviations of our mean. If you're looking at 3 standard deviations away from the mean, we can say that at least 89% of our data is within 3 standard deviations. At least is the minimum. It could be more. It could be 90, 91, 92%. We don't know the specifics, but this is a general rule of thumb when we're being conservative because we don't have a symmetrical bell-shaped distribution. Let's go ahead and work with the idea of standardized values. So recall my example earlier when I wanted to compare test scores of math students and Spanish students. Standardizing data values allows us to compare different things with different measures on a consistent scale, or a standardized scale. And so this is what we call our z-value or our z-score. So here is our z-score formulas, and again you'll notice that the process is similar for the population and sample. They just have different Greek letters, so you know that one is for the population and one is for a sample. So as you can see in both of them, when we convert, our x is their data value that we're working with, then we'll subtract it by the mean, whether it's a population mean or a sample mean, and then we divide it by our standard deviation. So for instance, IQ scores have a distribution that's thought to be bell-shaped, with a mean equal to 100 and standard deviation of 15. Suppose a person has an IQ of 121. Let's go ahead and calculate the standardized IQ then. So here's our mean of 100 and our standard deviation of 15. Here's my formula. So we'll plug in our x value, our variable of interest, which is the IQ of 121 points that this person received, minus our mean of 100 divided by our standard deviation of 15. That gives us a z-score of 1.4. In other words, a person with an IQ of 121 is 1.4 standard deviations higher than our population mean IQ. So this lets us compare this individual's score to our mean. Let's go ahead and do 53 from the textbook. Now you'll notice in this problem we're talking about samples, but the process is the same. So I've got my formula right over here for our samples z-score, where we'll take each of our x values minus the mean and divide it by our standard deviation. In other words, we're going to convert these x values into a standardized value, into a z-score. So in our story here, our sample mean is 1,000 and the sample standard deviation is 250. So plugging that into our formula, we'll first take our x of 800 minus our sample mean of 1,000 and then divide it by our standard deviation of 250. When we plug that into our calculator, we get negative 0.8. In other words, 800 is negative 0.8 standard deviations below the sample mean. In part B, our x value is 1200, so plugging that into our formula, we'll take 1200 minus our mean of 1000 and divide it by our standard deviation of 250. You'll notice my mean and standard deviation didn't change. The only thing that's changing is our x value, the thing we're trying to convert. So when I plug all of this into my calculator, I get a z-score of 0.8. In other words, 1200 is 0.8 standard deviations above the mean. Now, you'll notice I said below in part A and above in part B because negative tells us we're on the left side of our distribution. It's below the mean. And positive is above or greater than our mean. You can also look at our numbers here and understand 800 is below our mean of 1,000 and 1,200 is above our mean of 1,000. In part C, our x is 1,000. Let's go ahead and convert that. So plugging in 1,000 minus our sample mean and divided by our standard deviation, we get 0 because we are 0 standard deviations. We are exactly on the sample mean. So I'm right in the middle of my distribution. Make sure you have a good grasp on what it means to standardize data, as we will continue to do this for the rest of the semester. If you have any questions, just let me know.